On this worksheet, we're going to be doing a few different types of calculations that involve the energy that is either absorbed or emitted when an electron moves around in a hydrogen atom. The first problem is asking us to just predict which of these four transitions of electrons in a hydrogen atom would give off light with the shortest wavelength and the longest wavelength. So what we want to think about with this is that if we have a high value of energy, that's going to correspond to a little tiny short wavelength, something that can penetrate into your skin and your bones and do all kinds of damage. And it's also going to correspond to a high frequency, something that moves really fast and just kind of tears through everything. So high energy has teeny tiny wavelengths and really fast frequency. This problem is specifically asking us about the emission of light. We want to focus on that keyword. Light is emitted only when we go from a high energy level to a lower energy level. So that would be something like the first two transitions where we're going from a higher N to a lower N, a higher N to a lower N. If we're going up from a low N to a high N, that involves the absorption of light. So these two right here are not even an option. Both of those absorb light being absorbed. High energy corresponds to a big gap. There's too many arrows going on there. High energy is corresponding to a bigger gap between your energy levels. So when you're looking at these possible values, you're literally just looking at the gap between the two numbers, 5 versus 3 in 5 versus 2. Because 5 and 2 are further apart, this is a bigger gap, so that means this is going to have, of these two possible, that's going to have a higher energy, and that means that it will have the shorter wavelength. And this one, because these two energy levels are closer together, this is going to have the lower energy, which means that it will have, of these two, it will have the longer wavelength. The rest of the problems on this worksheet are harder. They are ones that involve the use of the Rydberg equation, which I have copied down here. Delta E equals negative 2.18 times 10 to the negative 18 times 1 over n final squared minus 1 over n initial squared. So this is the equation that we use to calculate the energy of the photons being absorbed or emitted by electrons that are moving around in a hydrogen atom. So first thing we have to do is figure out the 4 versus 2, where did they go in this equation, because it actually really does make a difference, not just in terms of the sign, but it matters. So this is saying it's going from n equals 4, which means that this is our initial, to n equals 2, so that means this would be our final. And so we're just going to plug that into this Rydberg equation at negative 2.18 times 10 to the negative 18 joules times 1 over n final squared. N final is 2, 2 squared is 4, minus 1 over n initial squared, n initial is 4, 4 squared is 16. So we get that right there. And then I'm just going to do all this math all at once. I'm going to do the parentheses first. 1 divided by 4 minus 1 divided by 16. I'm getting 0.1875 times negative 2.18 times 10 to the negative 18 joules. This gives me a negative 4.08. We'll say, times 10 to the negative 18 joules. Now, the negative sign right here in front of this 4.088, that's just telling us that the change in energy is negative. That just means that the electron is emitting a photon. So this negative sign is just another verification that we're actually emitting a photon, aka emitting or losing energy. For the rest of the calculations that we're going to do for this problem, we can go to an absolute value. So again, the negative sign here is just a way of communicating whether light is being absorbed or emitted. Once we know how much light is being absorbed or emitted, we can use absolute value. We need to convert the energy, we have energy right here, into wavelength. And to do that, we're going to use the equation E equals hc over lambda. I'm going to rearrange this equation Lambda equals hc over E. So I'm just doing a little bit of algebra there. So that I've got the wavelength variable isolated, and I can plug everything in. H is Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. This is a constant that we use a lot in this chapter. C is the speed of light, 3 times 10 to the 8 meters per second. And then E, this is where we plug in the energy that we just calculated, the absolute value of the energy. I'm just going to go with 4.09 times 10 to the negative 18 joules. Let's take a look at our units canceling. The joules will cancel, the seconds will be canceling, and we're going to be left in units of meters. 6.626 times 10 to the negative 34 times 3 times 10 to the 8 divided by 4.09 times 10 to the negative 18 is 4.86 times 10 to the negative 8 meters. The problem specifically asks for this to be in units of meters, or excuse me, nanometers. I feel like I did something wrong. Something is incorrect here, because this should be 486 nanometers, and this should be -7 meters. So let me just recrunch my numbers again. 6.626 times 10 to the negative 34 times 3 times 10 to the 8th divided by 4.09 times 10 to the negative 18. Still getting that. So let me recrunch these numbers. I probably made a mistake right here. 2.18 times 10 to the negative 18 times 1 over 4 minus 1 over 16. Yep, I got this exponent wrong. You probably caught that. You might be wondering, why did I know that the exponent was wrong? The only reason why I know is because I know that this transition corresponds to visible light, 4 to 2, and I know that visible light needs to have a wavelength of somewhere between like 4 and 700 nanometers. So that's the only way I knew that I'd got that wrong. The last question here is asking us what type of light this is, and I already kind of spoiled it by saying that it's visible light. But let's take a look at a table or a picture of the electromagnetic radiation spectrum so you can see how you would answer that question. Once you know the wavelength of light, or even if you know the frequency of light, you can go to a table of electromagnetic radiation. This one's not very pretty to look at, but it works perfectly fine. And you just find that wavelength on this particular table. 486, like I said, is corresponding to visible light. So that's down here in this colorful rainbow graph part. And 486 looks like it falls somewhere around blue. So this looks like this corresponds to blue visible light. The next question on here is asking us to convert this wavelength into frequency, and to do that, there's a couple ways that we could do that, but I'm going to use C equals lambda nu, the equation to calculate the speed of light. The frequency is C over wavelength. C is the speed of light, 3 times 10 to the 8th meters per second. And that frequency that we calculated, we want to use it in units of meters so that the meter unit can cancel out. 4.86 times 10 to the negative 7 meters. 3 times 10 to the 8th divided by 4.86 times 10 to the negative 7 is 6.17 times 10 to the 14. The way that we express the units of frequency, there's a few different options. You can go second to the -1, or you could also go 1 over seconds, or you could use hertz. They all represent the same thing, whatever you're most comfortable with. There's that. We're going to do those calculations again, so we're going to practice them all over again, basically the exact same thing, but we have different transition this time. So we're starting from n equals 1, so that's our n initial, 2n equals 7. That is our n final. Just to kind of save space, I'm just going to erase and write those numbers in. N final is 7. 7 squared is 49. N initial is 1. 1 squared is 1. So let's calculate this energy. 1 divided by 49 minus 1 over 1. That is negative 0.97959. And we're going to multiply that by negative 2.18 times 10 to the negative 18. And this gives us a positive 2.136 times 10 to the negative 18 joules. Positive because this time photon is being absorbed, so positive energy. Again, we want to transition or convert this to wavelength. Wavelength is hc over E. 6.626 times 10 to the negative 34 joules times seconds. 3 times 10 to the 8th meters per second. Again, both of those are constants. H and C are constants. And then our energy, 2.136 times 10 to the negative 18 joules. 6.626 times 10 to the negative 34 times 3 times 10 to the 8 divided by 2.136 times 10 to the negative 18. 9.3 times 10 to the negative 8 meters. We want to convert this one to nanometers again, so we want to multiply by 10 to the 9, divide by 10 to the negative 9, 93 nanometers. What type of light is this? Let's go back to that table again. This is not visible light because visible light ranges from 400 to 700. So what are we looking at? If we zoom in here, we can see the lines on this tell us that the ultraviolet spectrum starts at 10 nanometers, that's on the left-hand side, and then it goes to the beginning of the visible spectrum, which is a little under 400. So what we have, which is 93, that's going to be in that ultraviolet range. So this is UV, ultraviolet. And again, we want to calculate the frequency. Frequency is c over lambda. C is the speed of light, 3 times 10 to the 8 meters per second. Lambda in meters is 9.3 times 10 to the negative 8. 3 times 10 to the 8th divided by 9.3 times 10 to the negative 8. 3.23 times 10 to the 15, however you want to express the unit of frequency, second to the minus 1 or 1 over seconds or hertz. Now the last question on here is different and tricky. This one is telling us that an electron is making a transition to the n equals 2 state. So that means this is going to be our n final. The photon has a wavelength of 334. What is the initial energy? So what is Ni? So let's put in that n sub f value into this equation. 2 squared is 4. N sub I is what we're trying to figure out. We know the wavelength is 434 nanometers, and we are going to convert that into energy. So I'm going to actually write E equals hc over lambda. We're going to convert it into energy using this equation right here. H is Planck's constant, 6.626 times 10 to the negative 34 joules seconds. Speed of light is a constant, 3 times 10 to the 8th meters per second. And then we want our wavelength, 434 nanometers. 434 nanometers, we need that in meters, not nanometers. So we want to put a conversion factor with nanometers on the bottom, meters on the top. Nano is the prefix for 10 to the minus 9. That means 1 nano is 10 to the minus 9 meters, and we can just put it in that form, 434 times 10 to the negative 9 meters. Even though that's not normal scientific notation, it doesn't matter because it's all going to go into the calculator anyways. So taking a look at how the units cancel here, this is going to give us an answer in joules, which is what we want. 6.626 times 10 to the negative 34 times 10 to the negative 34 times 3 times 10 to the 8 divided by 434 times 10 to the negative 9. This gives us 4.58 times 10 to the negative 19 joules. That's what we're going to plug in over here. Now, we do need to be a little bit careful, so I'm going to put that number in. I'm actually just going to copy and magically stick the whole thing together. So we do want to be a little bit careful. Remember, the whole time I've been talking a little bit about the negative signs or the positive signs. We do need to make sure that we have the correct sign out here. Is it a positive sign or is it going to be a negative sign? And that information is given to us in the problem. It's telling us that a photon is being emitted. Photon being emitted, that means that the electron is losing energy. So we need a negative sign out there in front of that, in front of our energy. Emitted photon is a negative change in energy. So now all we have to do is solve for this n sub I. I think what I'm going to do is divide both sides by negative 2.18 times 10 to the negative 18 joules. That'll simplify this. Negative 2.18 times 10 to the negative 18 joules. So that's going to completely cancel out. And on the left-hand side, we have 0.210, and that's equal to 1/4 minus 1 over n initial squared. I think I'm going to subtract 1/4 from both sides. And that gives me a negative 0.0399 equals negative 1 over n initial squared. I can cancel out both of those negative signs, so I'll just erase those. And all that I have left to do is invert both sides of, well, I guess that's not all, but next thing we should do is invert both sides of the equation. So what I'm going to do is 1 over this, and that'll allow me to invert the 1 over n initial squared. So that is going to be 25 equals n, it's pretty much exactly 25, n initial squared, and that is pretty straightforward to solve. N initial is 5.